Team, in this section, I wanted to touch a little bit about torque. I haven't done a video yet about torque, and I think this problem is a good one to explain what torque is all about. So torque is a rotational force, and it is dependent on how far is a force being applied to the axis of rotation. In this case, it is pretty prevalent that the axis of rotation here is the origin, and it has a distance from the point of application, right here, to the axis of rotation, right here, okay? So the equation for torque is known as the cross product of the distance, R, and force. This cross product denotes that they have to be, that denotes that they have to be perpendicular to each other. And because they have to be perpendicular to each other, 90 degrees, that is the only way that we can analyze torque. So let's get on the bandwagon, and let's start off by identifying the torque in, actually let me just erase this really fast and say this is torque 1, torque 2, torque 3, and torque 4. With torque 1, I'm going to write down the equation. Torque 1, it is equal to the cross product of the radius r, 1, or the distance 1, cross product f1. We can rewrite it, since it's already 90 degrees, as torque 1 equals r cross product sine of 90 degrees. And because it's already 90 degrees, it's already perpendicular, it fares pretty easy, and you get the most out of your torque. See, like, you notice how I said the most out of your torque? If it's already 90 degrees from each other, that's the best that you can do in terms of torque. So we got this value. Well, torque equals, and I'll show you why pretty soon. 1. Okay, so we have that. Now let's go to torque 2. Torque 2, on the other hand, has an angle. Because it has an angle, the force, the component here that we want, because we want it to be perpendicular, is going to be a little bit less than the component for F2. The magnitude for F2. The component here, again, is going to be a little bit less than the magnitude for F2. And notice that I put X direction, because we want the force in the X direction for this one to make it completely perpendicular. Because remember, just to identify, this is how we want it in the end. Okay? So you can go about it two ways. We can put it, there's an angle, 30, right here. And we know that we need it 90 degrees. And we can put it tail to tail. So instead of leaving the R here, a vector here, remember, we can move vectors. We can move vectors into the position that we want, as long as they follow the same magnitude and direction. And now it's tail to tail. Since I want it 90 degrees, I can rewrite this as R times R2 times force 2 sine of 120, or let me just, so I don't miss a step, sine of 90, which is what I want, plus 30 degrees, which is the additional angle that I have for it. And that would give me R force sine of 120. Okay? That is a way to do it. Another way to do it is by identifying that you need both vectors to be completely perpendicular to each other. So you can just go and say, okay, this is an angle 30, and I need the component of f in this coordinate. So that means I can rewrite it as f of x equals f cosine of 30. And then you just multiply r to get the torque. Let me just put it here, torque. Because they're now completely perpendicular to each other. That is another way to do it. Those are options. Okay? But let's say, like, before we continue, let's say that F2 and F1 are equal to each other. Let's say that F2 and F1 are equal to each other. So that means that we have RF 1, and then over here we have RF 2 sine of 120. Because they're equal to each other, but now we have something that we have to consider, sine of 120. Because it's sine of 120, I believe that the angle is, I'm doing the calculation in my phone, give me a second. We believe the angle is the square root of 3 over 2. Already, this right here diminishes the potency of the torque because it is at an angle. Whereas this one maintains the strongest torque. Just because you put an angle in it, already the force that you're applying in it is weaker than when you have it perpendicular. So, in effect, the torque without the angle is going to be larger than the torque or the force being applied with an angle. Okay? Let me erase this. Okay, now let's continue with F3. F3, torque. So in this one, it's interesting. Notice how it is coming straight to the origin. It has no distance from the axis of rotation. Remember what I said in the last video I made, where if there is no distance from the axis of rotation, this is 0. Thus, torque is 0. Sorry, here we go. Torque is 0. If this line, let's say it like this, if the origin is over here, right, and the vector is right here. This is force. Notice how it is completely parallel to my distance. If it is completely parallel to my distance too, it means that this is still, torque is still 0. Because, if I erase this, when we do it, r squared to, let's just, oh, not 3, sorry, 3, sine of 0 is 0, because there is no angle, there we go, there's no angle that affects the torque. The angle is 0, so there's no torque whatsoever. Okay, identify that. So F3 is 0. Then we go to F4, torque 4. So torque 4 is acting with an angle of 20. And just like we talked about before, we can redo this. We can write down that this is the distance r, is going downwards, F4, at an angle of 20. We can do tail to tail. Move this right here. And since we need the 90 degrees for the perpendicular, this is 90 degrees, we just have to add the 20 degrees right here to make it so, and now we have 100 sine of 110. So it would be R4, R3, R3, R2, R4 times force 4 sine of 120, or 90 plus 20. And it's not 120, it's 110. Okay? And now you have identified all the torques, all the separate torques acting on the system. Okay? But let's think about this. It's saying that this is out of the page at the origin. So if it's out of the page, it means that it is coming out of the page and the direction of motion is clockwise. I mean counterclockwise, I'm so sorry. Counterclockwise. Do this. Point your index fingers in the arrow that I just created, and your thumb should be coming out of the page. That's the right-hand rule for torque. Because it is positive counterclockwise, it means that we have to identify all the torques that are positive and negative. So for torque 1, it is going against the counterclockwise motion, where F1 is, so that means that torque 1 is negative. For torque 2, and I'm going to just, instead of doing that, I'm just going to write it right here. Torque 1, negative. For torque 2, it is positive because it's going in the motion of counterclockwise. Positive torque 2. Torque 3 is 0, so we don't have to worry about that. But torque 4 is negative because it is going against going against the counterclockwise motion. That all equals to, and let me just make sure I calculate another page at the origin, to the sum of all external force torques and you sum these up to get the sum of all external forces. Okay, to calculate the torque about the x-axis. And you do that by summing up all the torques up that you find here. And you're done with this problem. All right, I hope this video was helpful for torque. And let me know if you have any questions. Email me if you have any questions.